So hello, welcome, good afternoon. Thanks for joining me for my session. My name is Jan. I'm working for the Open Source Automation Development Lab. We are a registered German cooperative and we support our members in using open source in their products. This pretty much includes legal services and technical services as well. A topic which has been with us for many, many years is Linux in real-time. And this is something I'm going to talk about today, specifically real-time communication. So we're going to look into how you could set up real-time Ethernet and TSN with Linux. So TSN stands for time-sensitive networking. It's pretty much a set of quite a few standards that aim to enable real-time Ethernet communication with more or less standard components. And there's actually quite a few bits and pieces available in Linux, so you can already do a lot. But if you have tried it before, you might have realized it's not really straightforward to set up. And that was the reason why I tried to put together a kind of a quick start guide and tell you what you really need to do. So before we get started, let's think a bit about the setup. So what do we want to achieve? And I picked a simple example, so we'll just do a peer-to-peer setup. But don't be disappointed. I can assure you it's going to be sufficiently complicated. So there's quite a few things we need to take into account here, but let's see how that goes. So basically what we want to do, we have a peer-to-peer connection between two Linux machines, and we want to have time-critical and non-time critical traffic on the same wire over the same interface, and we just want to sort that out, and we want to avoid any interference between the non-critical and the critical traffic. So what do we need for this, right? So first of all, since we want to have real-time communication, obviously we need a real-time capable operating system, so we enable preempt RT in both machines. So this is pretty much the starting point. Another topic we need to look into is, I mean, it depends on your use case, but what you usually need if you have real-time Ethernet communication, you need time synchronization between the systems, right? NTP is not sufficient here. You need to have something with higher precision. So we're going to look into the precision time protocol and how you can use that with Linux. Now, we need to think about an imaginary example, what we want to do. So what I thought about is we're going to have PTP traffic on the wire. We're going to have time-critical traffic on the wire. And we will have just a few other things going on, right? And we still want to have timing guarantees. What we usually do for that is modern NICs usually have a few features. So most importantly, you usually have different queues for sending and receiving network packets, right? So what we want to do is we just want to send and receive critical and non-critical traffic through different hardware queues and configure that accordingly, right? And so we need to do that on both sides. So we have one queue for the critical traffic. We want to reserve one queue for the time synchronization traffic. And then we're going to reserve two hardware queues for anything else which is going on. And not to forget, and this is really important, we will need to talk about VLAN, because each and anyone in the network should be aware about critical, non-critical traffic, right? It's like sending a letter for an express letter. If you send that by mail, it's marked as an express letter, right? So we need to do the same with a network packet, because every component in the network needs to know, is this important or not, right? So this is pretty much the picture we want to draw together within the next 30 minutes. Okay, so let's get started. And as always, we start with the basis, right? So I told you we need the real-time operating system. This sounds simple, but please do this with care. Because if that doesn't work, I mean, the real-time communication cannot work at all. So please do not try to build your house from starting with the second floor downwards, right? I mean, you usually start building from bottom up, so we're going to do that with that setup as well. We could spend the whole presentation in tweaking real-time behavior, right? So I just wanted to focus here on one specific setting I'd like to make use of. So what I want to do is I want to isolate pretty much two CPU cores to deal with the critical network traffic and do the relevant calculations, right? And the other CPU cores we have available can do anything else. So this is just what I wanted to mention here. There's several ways for that. I'm just using the current command line here. There's way more you you should take care of when setting up a real-time system, like power management and whatever could cause bad latencies, right? If you want to do some further reading, you can point your browser to realtimelinux.org. There's a few starting points. I recently wrote a quick start guide. Just feel free to take that and take the necessary steps to set up your real-time Linux. At the end of the day, what we wanted to do is we want to evaluate the behavior of the base systems on both sides, right? We want to measure the latencies we can achieve. There's many ways to do that, right? So you can use the Swiss Army knife of real-time measurements. You can use cyclic test. There's other methods as well these days. You can use the time-alert tracer with RTLA, which is pretty nice because it's kind of a kernel built-in cyclic test, right? And it can also help you to figure out the root cause of latency, right? And it is really important. I mean, do not measure just for 5 minutes. So you should get enough samples to get a good idea about real-time behavior. So at the end of the day, what we expect is that we want to see that we can give some real-time guarantees on the system. I marked here the worst latency I observed in this measurement, which was 66 microseconds. We will need to remember that number later. So we'll come back to that. Just remember the 66 microseconds here. So just let's assume we have now 2 machines running preempt RT. Everything is going fine. So in the next step, we can start setting up the hardware configuration, right? And if you remember the picture I drew in the beginning, so we wanted to have 4 hardware queues on both sides, right? So we need to configure that. So it really depends on your device you are using. For configuring hardware queues, ETH tool is usually your friend. So in this example, I'm going to use 4 combined queues. So combined queues means we are using these for sending and receiving packages, and we set up the queue size. So this is pretty much what we want to do. So you see this is actually quite simple. Another important thing is, depending on your hardware, I briefly mentioned power management when it comes to real-time. Modern NICs usually also have some energy efficiency functionalities. These might cause really relevant latency, so usually might want to disable these as well. So if you want to disable energy efficiency for your NIC, you can also just use ETH tool. So this is pretty much simple setup, going it step by step. Well, now let's dive into the topic a bit deeper. So we have the basis, we have 4 hardware queues. Now we need to find a way how we could tell Linux what should be sent through a specific hardware queue, right? And the idea here is basically that we define so-called traffic classes. These traffic classes are mapped to socket priorities, right? So socket priority goes to a traffic class, and then the traffic class is assigned to 1 or more hardware queues, right? So it's socket, traffic class, hardware queue. This is pretty much what you need to do in this setup, right? To do so, you need the good old TC command. If you have used TC before, you might know that the syntax is sometimes not really straightforward, right? So I would like to spend a moment on that to explain a bit further what you need to do. It might look a bit weird at the first glance. I mean, you don't want to know how many hours of reading man pages it took me. But I have to admit, it's really well documented. So that's yeah. Okay. So I think the first setting here. So we're using a queuing discipline which is called MQ-prio. With that, we can set up a number of traffic classes. Remember, we had 3 traffic classes, critical traffic. We wanted to have one for PTP and another one for all the non-critical traffic. So 3 traffic classes. That's easy to understand. Now the mapping needs a bit of explaining, because now we are mapping the socket priorities to the traffic classes. And this goes as follows. So the position of the number is basically the socket priority. So we have 15 socket priorities available. So this position is priority 0. This is priority 1. This is priority 2. This is priority 15, right? The number you write down here is the traffic class. So that means socket priority 0 is going to be mapped to traffic class 2. socket priority 2 maps to traffic class 1, and priority 3 maps to traffic class 0, and so on, right? So this is the first kind of mapping. So if you get into that once, it's okay, but I think that this really needs some explanation to get into that, right? So we have the first mapping, socket priority to a specific traffic class, and now if you want to decide if we send critical or non-critical traffic, we do that via the socket priority. Now in the next step, we want to map these traffic classes to the hardware queues we have set up before, right? Now, once again, the position matters, right? So first position is traffic class 0. Second position is traffic class 1. Third position is traffic class 2, right? Now let's look into the numbers, what these really mean. So I'll try to do that with a picture. So what we say here is that traffic class 0 goes into one queue. So the first number is the number of hardware queues we want to reserve for that traffic class, right? And the second number is the offset. So at the end of the day, what we do here, traffic class 0 goes into one queue at offset 0. Same here, traffic class 1 goes into one queue starting from Q1, and then traffic class 2 goes into two queues starting from Q2, right? So number of queues and the offset. That's pretty much what we do here. And now we have set up the chain. So socket priority, traffic class to the hardware queue, right? So, I mean, we already managed to do a very important step to send out the traffic through the right queue. Some devices can do hardware offloading here. So this really depends what you have available. So if you want to do hardware offloading for that, you could tell right here. Okay. Hardware queues. Let's quickly come back to the operating system right here. Now you might wonder why I didn't deal with all the relevant steps in the very beginning, right? So the thing is that depending on the number of queues you're going to set up, you will have a different number of interrupt threads or NAPI threads for that device. So we will see one interrupt thread and one NAPI thread for each hardware queue we have set up, right? And for the critical traffic, we want to have the appropriate priority for these, right? Because by default, as you know, all interrupt threads come up with the same priority. They would be SCAD 5 or 50. So for our critical traffic, we want to do two things. So we want to move them up in priority, and we want to route them to the isolated CPUs, right? So for the IRQ routing, it's basically like if you set up the IRQ routing, the IRQ threads will automatically follow, just to avoid that you have any cross CPU wake-ups, right? There's just a few details you need to know. Actually, I mentioned that in the blog post I mentioned before, so if you just want to have some more details, go there, do a bit of reading. Mentioning just right here how you could enable NAPI threading for a device. But at the end of the day, what we do want to achieve is something like this. So I just marked in the process list the relevant threads for my critical hardware queues, right? And I did two things. I moved them up in priority. So basically, most of these get SCAD 598, and I pinned them on CPU 2, which I isolated before, right? To get slightly better reaction times, right? That's basically it. Okay? Getting closer. But we're not done yet, right? So I promise this is going to be sufficiently complicated. Now we have a way to route the traffic. This is really important, right? Now, usually we need to decide how we want to schedule the traffic, right? So there might be different scenarios. We don't want to have collisions on the bus, right? So for that purpose, there are several queuing disciplines available. How you could tell the packet scheduler how and when you want to send specific traffic. There's quite a few. I'm gonna show you two examples, right? And the first one, I think that was the first one which was integrated in mainline when it came to the TSN features, is ETF. It's the earliest transmit time first. So the basic idea here is that whenever you send a packet with that queuing discipline, it gets assigned a send time, right? So you say when this packet should be sent on the wire. So this is something you could do. What you need to see here, I'm having a handle this is the handle of the MQ prio QDisk I have said before. So usually you have ETF on top of MQ prio, right? So this is something you do in addition. Then the second number, so this is a bit weird because now numbering starts with 1 and not with 0. So the 1 here tells us this is traffic class 0, right? So we now decide for which traffic class we really want to use ETF, right? Okay. Then we need to tell which clock we want to use. So basically, we have not much options here. We're going to use clock tie. And what's interesting here is that we can take the scheduling latency into account, because we know there might be some scheduling latency for our application. So it might take some time that we can bring the data from the user land to the kernel, right? And I can take that latency into account. You remember where we got this number from? Okay, so this is in nanoseconds. These are the 66 microseconds worst case latency we evaluated on the platform. So this is also the reason why I told you really need to do your homework first before you continue with the rest of the setup. So the main idea here is pretty simple. To calculate the next wake up time, you subtract the delta from the next TX time, right? So you take the scheduling latency into account. Most importantly here, modern NICs, many modern NICs, support a send time in hardware, right? So you don't have to rely on a system timer. So you synchronize the time over the network interfaces, and the network interface itself could send a packet at a specific time. This is what we call the launch time feature. If your network card has this capability, you can just put offload here, and then we would offload all the work. So this makes it pretty accurate. If you don't have that, we would use a system timer, but well, then accuracy suffers quite a lot, right? So this is pretty much how we would do ETF. The other example I prepared is the time-aware priority shaper. It's another queuing discipline, TA prio. This is pretty much standalone. So what you would need, so it implements a simplified version of the so-called scheduling state machine. With setting up TA prio, you would do everything in one go. So we define the number of traffic classes, map the socket priorities, and so on. I'm not going to mention that again, right? So I explained that before, so it looks pretty much the same. But most importantly, what TA prio does is it defines a sequence of gate states for traffic classes. And that means that you could assign a schedule, which means that you could say for 100 microseconds, I want to send traffic class 0. For another 200 microseconds, I want to send traffic class 1, and so on and so on. And once again, good old TC command helps us here. So we covered this before, so I'm just going to explain what's specific for TA prio. So the base time setting basically tells at what time you want to start with schedule. So you could start right now, or you could start at any time in the future. So pretty depends on your use case. The most important part here is the SCAD entries. So every SCAD entry comes with a command. So this is basically the S stands for set gate states. And now the second number defines the traffic class, which will be scheduled right here with that gate. And right here, it's a bit mask. Yeah, sorry for that. It's like it is. It's a bit mask. The idea is that you could even combine traffic classes in one schedule. So most probably that was the reason why they decided to make it a bit mask. So that means the 1 here stands for traffic class 0. The 2 is traffic class 1, and the 4 is traffic class 2. And the number at the very end, is the time, is the schedule, right? So what we do with this setting, traffic class 0 will be scheduled for 200 microseconds, and then it won't be sent, right? Then the next gate opens. We have reserved 150 microseconds for traffic class 1, and we have reserved another 100 microseconds for traffic class 2. So at the very end of the presentation, I will show you a way how you could evaluate if your schedule is working, how you set it up, right? So last but not least, also here, you have the possibility that you can offload to your hardware, because many modern NICs even have the possibility that you could tell them a schedule in hardware. That also makes it pretty accurate. if you're in the unlucky situation that you don't have that feature, you could use the so-called TX assist feature, which will then make use of ETF to put the schedule. So then if you're still a bit lucky, you might have a hardware that supports ETF, and then it's completely, once again, based on a system timer, right? Obviously, the flags here are mutually exclusive. So either you use a system timer or you use, either you use TX assist or you use a schedule that is offered by your NIC. I think that's quite clear. So I just wanted to briefly mention, if you want to use TX assist, how you could do that, because there's at least one minor pitfall you should be aware of when you do that. So if you don't have a hardware that can do the schedule on its own, what you could do is you use the TX assist feature, which is marked with the flag 1, right? And then you need 2 additional parameters. So once again, you can take the scheduling latency into account, which is 66 microseconds, and you need to provide a clock ID, like we did before with ETF. So we need to tell which clock is being used for the scheduling of the network packets, right? So this is pretty much what you would do. And then on top of that, so you see here we have the handle 100 assigned here. On top of that, you would need to set up ETF on top of TA prior, right? Because ETF now would be used to do the schedule, because the hardware won't do it for us. This is pretty much like we did it before, right? Now you might spot one parameter I added here. So skip sock check. Might sound a bit weird. The thing is basically that, and I mean this is quite logical, that if you do a socket with with ETF, by default every packet that hasn't a SOTX time assigned or doesn't have a send time assigned will be dropped silently, because, well, we don't know how and when to send it, right? But in that specific situation, there's actually no socket associated, because the packet is coming from another queuing discipline. So it would be dropped, right? So we want to skip that check, and we would need to explicitly tell that we want to skip that check. And this is actually a major pitfall. So if you forget that, packages would be just silently lost, right? So this is why I wanted to, I mean, you can imagine this made me scratching my head for a few hours. This is why I wanted to mention it to you. So you don't have to spend that time, right? Okay. This is packet scheduling. This just, I mean, there's way more packet schedulers, right? I mean, you can do many things, but these are the 2 most common examples when it comes to real-time Ethernet communication. The next steps are basically needed for receiving packets, because everything we have done so far basically was to define how packets are sent to the network, right? So we defined how they go out, via which traffic queue, at what time they should be sent. Now the thing is, the receiver needs to have some kind of information, is this a important packet or not, right? And for that purpose, we basically have just one option, mostly one option. We need to set up a VLAN to send the traffic, because for VLAN, you know that the packet can has a priority field, right? So all the network components in between can look at the priority field and then decide what to do with the traffic. So we need to set up a VLAN. I think that's easy peasy, so we can cover this very briefly. But what is important right now, we need to do, you might have guessed it, one more mapping. So we did already a lot of mappings before. So last mapping we need to do is the so-called egress mapping for the VLAN. So basically the idea is that with the socket priority, you can now also decide what would be the VLAN priority of a packet, right? And so it's as simple as that. So with the egress policy would basically say, whenever we use socket priority 2, I want to put 2 in the PCP field, so it's VLAN priority 2, and so on and so on. So when the packet goes out, you have this additional information that any participant in the network can look at the PCP field and then decide what to do with the traffic. This is important, because otherwise, if you send out the packet, that information would just be lost, right? So this is just with the express letter. Like the postman needs to know that this is a express letter, right? So you need to write it down somehow. And this is what we need here, what we do here. Okay. Getting close. Getting close. Now packets are going out. They are marked correctly. Now we're the postman who needs to read that this is a express letter. There's actually quite a few options you have here. Many network interfaces do have also offer offloading for that. So this is what I'm going to use because it's easy to use and it's fast to explain. Another option I just wanted to mention is you can also use eBPF and XDP. Right. So what you could do, or what many people do is, and what works very efficient is that you write an XDP program which basically parses the data coming in, looks at the PCP field, and then decide what to do. So if it's non-critical traffic, then you just return XDP pass and just pass it on to the network stack. If it's critical traffic, you could, for example, put the data into a memory map and just send it straight to a user space application or whatever you want to do, right? So XDP is one option here. I made, in this example, use of some hardware features on the NIC. Once again, using ETH tool. So the syntax here is basically, I'm telling with a bit mask, okay, look into the PCP field. If this is 3, then the action is 0, which means whenever PCP field is 3, this should go to hardware queue 0, right? So what we did for the sending side before, we're now doing for the receiver side. And the same here. When we see PCP field 2, we send that to hardware queue 1. And for all other PCP values, we would send it to hardware queue 2 and 3, right? So now we completely sorted things out, sending it out via the correct hardware queue, and on the receiver side, we look at the PCP field and we put it to the correct hardware queue. And you remember that we prioritize the relevant NAPI and interrupt threads so that we make sure that everything is scheduled in time. So we covered basically both directions of sending packages around, right? Last but not least, we've got 2 critical traffic classes, right? So one was just random traffic. The other one was reserved for time synchronization, right? And this is the last topic I wanted to cover. How can you do the time synchronization between both systems? We want to use PTP. Usually with Linux, you do that with the Linux PTP package. This is available for all major Linux distributions, and at the end of the day, it's quite easy to use. So last but not least, that's the easy one. So I kept that for the end of the presentation. The easy stuff. The idea basically here is that, I mean, you have a grandmaster which provides the time to all the participants in the network. So everyone on the network can agree on the same timing, right? So what you assume is that the grandmaster is deriving the timing from a high precision time source and then can provide that to the other participants in the network, right? I mean, you can download the slides, right? So this is pretty much how that would look like. So you have 2 commands, the PTP and the PHT2sys. So in this case with PHT2sys, we take the system time and we synchronize that to the network interface. And then with PTP for Linux, we distribute that over the network, right? Most importantly here, you might spot that I put the socket priority here because the idea was that we have one reserved hardware queue for that traffic, right? And I want to achieve that by doing the appropriate socket priority because we have defined a mapping for that before, right? Every participant on the network, all the clients, do pretty much the same, but I mean, they would get with PTP for Linux the time from the network and then set their local clock accordingly, right? This is, I mean, at the end of the day, pretty much what you need to do. You can have as many participants you want to have. If there's more than one master, they could even agree who's the most accurate one and so on and so on. So I think also PTP is pretty well documented, right? So this is the time synchronization part. Okay. Setup done. Just took 30 minutes. Okay, now we can evaluate. So this is, I mean, evaluation can also be a tough part because there's many steps that could go wrong, right? So it really depends on what you want to look into later on. There's a open source project which is called the RTC test bench, was formerly called the TSN test bench. It's available on GitHub. It offers a lot of pre-built tests for a peer-to-peer setup, including the setup. right? So, I mean, they have scripts and everything. So everything I did manually right here is covered there. There's a lot of examples with different workloads. So you could, they have OPCOA pub/sub examples and a few others where you could just measure round trip times. So if you have a more complex setup and want to measure the round trip times and stuff, this is something I would like to recommend to you, right? For this presentation, I took 2 simple evaluations, right? And a very common thing is, or the first thing people want to look into, how accurate the time synchronization is working, right? You could actually do that with hardware, right? Because many network interfaces offer a PPS signal. So you could take that from the different devices, just put a scope and see how accurate the synchronization is. The easiest one is that the participants on the network will basically tell you what's the calculated offset from the master, right? So this is the default mode with Linux PTP. So it would tell in the logs what's the offset. These numbers are actually nanoseconds, right? So in this case, we're in a range of 10 nanoseconds, which is honestly not always the case, right? But realistic values are really, you could get to low microsecond or sub-microsecond synchronization. So this is really possible with PTP, even with heavy load on the network, right? You could do actually the same evaluation during runtime. So Linux PTP comes with a command which is called PMC. So you could fetch several values during runtime. In this case, we're just asking for the current data set, and we can see here the current offset from the master in the network is 26 nanoseconds time difference. So this is really what you need to have high accuracy time synchronization between devices, right? So that's quite easy to evaluate. The other one I wanted to tell is, because I got this question quite a lot, how can I verify a defined schedule, right? There's many options here. You could capture the traffic with Wireshark or TCP dump, but a quite nice, actually quite old tool is a tool called plget, which just sends traffic around and can do a couple of measurements. Can also take hardware timestamps and tell you where time is lost, right? How much time is spent inside the driver, how much time is spent on the wire, and so on and so on. One easy test you could actually do is, as you can see here, this is the recipient side. And I just tell plget, okay, I'm expecting that we have incoming UDP traffic on port 5000 on a specific network interface, and I'm expecting 16 packages. After 16 packages, I'm going to stop the measurement. And with the IP gap option, I basically tell I want to measure the delta between the incoming packages on that interface. And this is pretty much what you could use to check if you're following the expected schedule. Because on the sender side, what we could do is, if we start a package generator, we put a socket priority, so we can define under which schedule things should be sent, right? We also say it's UDP, it's going to be on port 5000. We're going to send 16 packages, and the L option is pretty much the packet size. So given a bandwidth of 1 gigabit, I think this should be something like 12 microseconds. If you just send as fast as possible, right? So what would happen here is the sender would send 16 packages with that size. The receiver would measure the delta, and after 16 packages, it would print out the delta between the received data, right? And this is the result in this example. So, okay, we received roughly 8 packets with a delta of roughly 12 microseconds. This was pretty much what I expected with a 1 gigabit connection. But now, if we have a closer look, you might have spotted this, even without highlighting. So we have one packet where we have a gap of 400 microseconds. And this is what I expected. Why? Remember the schedule I have set up before. So we have defined several traffic classes, right? So we had 8 packets coming in at 12 microseconds. So that's 96 microseconds. So we're close to 100 microseconds. So this is pretty much the schedule I defined here, right? Now the gate is closed, and the other traffic classes will be sent. And these are 150 microseconds and 250. So 150 plus 250 is roughly 400 microseconds. And then we are back to the first traffic class, right? And we start sending in time. So this is a very simple method to evaluate that we are kind of following the schedule we wanted to see, right? It's pretty simple, pretty efficient. There's way more you could possibly do, but it's a simple, straightforward tool. And that's why I wanted to mention it, right? So there is way more that I could tell, actually. You now might have an impression why I started with a peer-to-peer setup. So because there's quite a few steps. And I mean, you can imagine that we have now 2 participants on the network and they need to have the same schedule, right? So the setup needs to match. And now with every participant, you can imagine that things get more complex and they usually don't want to do that by hand. So people are, there's discussions on how you could optimize the configuration, but I think this is in the TSN area still the biggest part of discussion, how configuration should basically look like, and looking at these steps you get an idea, but this might be the biggest part of discussion. So this is pretty much what I wanted to tell you today. So I wanted to spare you some reading of man pages and summarizing this on some slides. So I hope this was helpful for you. I'll be around for the rest of the day, so keep on asking questions, send us ideas. By the way, I mentioned the real-time Linux org page, so we just started a new web page. So if there's anything you want to see there, if you have any hints for us, just let us know. And thank you so much for attending my presentation. And I think we still have 3 minutes for questions. So there will, well, let me...
So thanks for the fantastic introduction. The way I understood it, the only real crucial hardware capability that you need in order to get started is hardware queues, right? The other things can be somewhat done in software with sacrifices to precision or accuracy, right?
Yes. So there's the other one is basically the time synchronization part. Yeah. So, but I mean, most modern hardware is aware of the time synchronization. The only really crucial feature is basically the hardware queues, because otherwise, I mean, it's really hard to get traffic in time. For all the rest, you can basically set up, but I mean, the accuracy is not that good as you could do in hardware, but that's right, yeah.
Thanks.
For the embedded users, you should use 5088 PHYs though, otherwise you don't have PTP. So.
That's right there.
When you've got switches in the network, what effect does that have on the? I mean, yeah.
You know, there's a reason why I started with a peer-to-peer setup. You need, I mean, the switches need to be aware of the time synchronization. So you cannot take any random switch. Then definitely you need the appropriate switch configuration. So what we set up on every client using the VLAN priorities needs also be to set up on the switches that are in between, because otherwise also, I mean, you might have a bottleneck that doesn't work out at the end of the day. So there's, I mean, the hardware features that are crucial for each participant also need to be there in the switch, and you need to have, I mean, the switch also has to be aware about the schedule and the VLAN priorities and so on and so on.
With queues as well then?
Not necessarily with the queues, but it's important that it would route the traffic accordingly. So it looks at the priorities and routes the critical packages first.
Okay.
Yeah. So you cannot take any random switch. Yeah.
That's what was my question. How common are switches that support?
Oh, well, from my experience, not pretty common. So the most of the hardware I know is actually pretty expensive. So, but there might be other people in the round which have more experience with the switches, but I think availability is still pretty limited on the market. But that's at least my experience, right?
There's a lab in Germany. There's compatibility testing.
Yeah, so the comment was basically there's a lab in Germany testing different devices. There's quite a few. So there's what I could mention is the University of Stuttgart, the ISW. So they have a TSN test bed, and they do plug fests on a regular basis where you could just bring your devices, put them together, and test like switches and stuff if it works the way you would expect it. Yeah. So one last question. And then I'll be around here, so we can continue in the break.
So there's one main simplification in this back-to-back setup. So you only have to deal with one PTP domain for Linux.
Yeah.
And we had, so I stopped looking into TSN 1 year ago, so I had not the chance to catch up. So question to that. There are auxiliary clocks, meanwhile, available in Linux because you have to synchronize your host clock against your single PTP domain. And when you have multiple of them, this trick, so to say, does not work any longer.
Exactly.
So did you play around with that already?
Not so far. I mean, the auxiliary clocks are quite new. This was a big miss so far, right? They are quite new. No, I haven't had the chance to play around with that, but this is on the to-do list. Okay, unfortunately, time is over, but we can just keep on discussing the break. So once again, thank you so much and have a great rest of the conference.